Your device, you don't have many moving parts compared to the commercial.
That's correct.
And so what have you done to get the same benefits?
Okay, so that the resin will be absorbed onto the yarn, and then after the resin is absorbed, really what we want to use that infused yarn with is to wind it around the bottle. Okay, so in a very short distance, we're able to achieve that. It's in about a couple of feet, right? We're able to see that process right away.
Now that you have the process that has been miniaturized, what is the next step?
So in order to, it needs to be, so those steps that we have defined and optimized are now going to be transferred to a space flight center, which is used to building these types of flight articles. And those basic steps are basically now being adapted back to a commercial machine.
And then from there, that pressure vessel will be transferred to the flight facility where it will be launched on a sounding rocket in 2016.
Correct. We're going to be launching from Wallops, yes.
Now, nanotechnology began several years ago. Well, it's been around for a while, but from where you started with it, how has it evolved over the years?
When we started working with carbon nanotubes, they were still available in powder form. And because on the nanoscale they had such tremendous properties, people thought we could just essentially sprinkle some on a polymer matrix and get the benefit of these materials. We studied it for several years and realized that is not a method that we can get the type of properties that we're looking for, because we're competing with state-of-the-art structural materials, which are carbon fiber composites. So around 5 years ago, we actually switched approach and worked with a vendor so that we use predominantly continuous format of carbon nanotubes. Now, the challenge there is that in the bulk form, it does not have the kind of properties that were existing in the nanoscale. We had to basically optimize the process to take advantage of these processes and work in collaboration with the manufacturer to also optimize those properties from the starting material. So they had to modify their production process to accommodate this. And so there was interactive exchange of information so that we can both get better material properties. In a span of about 3 years, we've made significant advances that take us far from where we started, to the degree that I can say that just 2 years ago we did not have the kind of properties we have now.
And where do you see the future, or how close are you into perfecting carbon nano composites?
So
that's kind of a big question.
Perfection, yes, perfection is hard to achieve. So here's the thing. When you talk about perfection, we are comparing against a material that's been around for about 50 years, right? Although we've come a long way when we actually analyze the materials that we have now for carbon nanotubes, they're nowhere near optimal. The good news is, despite them not being optimal, they're already performing at par with some carbon fiber composites, right? There's a lot of upside to this material that we don't fully understand at this point. And so there's very large areas of research yet that we can explore to really tap the potential of this material.
Now, earlier, Steve Gaddis said that they are working for a high reward from high risk. What is the reward you're looking for from carbon nanotube composites?
When we first started looking at carbon nanotubes, the reason we're looking at it is because there's high potential for this material to be a disruptive technology. And the reason is it is multiple times stronger and stiffer than carbon fiber. What we're trying to do now is we are looking to optimize it so that it is at least 2 or 3 times stronger yet than what is possible now. And the reason is there are some applications like access to space, especially if we're going to Mars, where significant reduction of mass is very important, because what you launch is hundreds of times heavier than what your actual payload is. So we're trying to reduce the mass of the payload. If we can get 2 to 3 times stronger than state-of-the-art material, it makes a mission to Mars possible. And that's why we say this is a disruptive technology.
And that is game-changing.
Yes.
You're watching NASA Edge.
An inside and outside look at all things NASA.
minus 5, 4, 3, 2, 1. Go for main engine start. 0 and lift off.
This is no ordinary aircraft, and on board is no ordinary spacecraft. This C-5 Super Galaxy is hauling something special.
It can carry what no other airplane can carry in the Air Force. Width, length, weight, you name it can get on that thing. This jet can do it like no other jet.
After 2 years of construction at Lockheed Martin in Denver and a few hours in the air, NOAA's GOES-S has finally made it to Kennedy Space Center, where the countdown to T0 begins.
It's always exciting to bring a satellite down to Kennedy Space Center and participate in that whole activity of getting a satellite ready for launch. Getting it out here and rolling it into the launch processing facility, that is a very big deal for us. It's one of the hugest milestones in any spacecraft program is shipped. It's not easy to transport something like this across the country.
And this is where the rubber meets the road. This is where all these people that have worked on this program for a couple years, it culminates into the excitement of getting ready for what we call launch fever.
And so now, we get to kind of do some of the fun stuff, like put it on a giant airplane and take it to Kennedy Space Center, where we get to prepare it to go onto an Atlas V launch vehicle and launch.
It's the job of NASA's Launch Services Program to get GOES-S into orbit. And they have just a few months to do the final launch preps and inspections before T0 arrives. This is no easy task with a spacecraft of this size and complexity. In spaceflight, there are no second chances. A successful launch is resting on their shoulders. It has to be perfect the first time.
It's very exciting. I love being a part of this, and I love being able to contribute to the spacecraft and to its success.
GOES-S is the second part of a weather satellite upgrade project NOAA is undertaking, destined to save lives by modernizing our weather forecasting ability.
We have a very young team, and this will be their first campaign. So we're trying to put the excitement into that, let them feel what it's like to touch the spacecraft for the last time. Launch operations is time we all get together for one goal, which is launch.
But achieving that goal will not be easy. The road to T0 has just begun. There's only one cargo ship designed to transport rockets for United Launch Alliance. And tonight, it's pulling into Port Canaveral with the robust flight hardware of an Atlas V.
We're a high-tech vessel, high maneuverability. We have to be because we get into some tight areas on shallow rivers. The Delta Mariner is unique. It has 2 aft Z drives coupled by computer with the bow thrusters that turns 360 degrees on demand.
This crew has work to do. In less than 4 weeks, the rocket must be safely delivered, inspected, and assembled in order to successfully launch NOAA's highly advanced GOES-S weather satellite.
I sense from the crew the pride being part of this mission. And when I put this vessel alongside the dock, it is a very accomplished feeling that we all have.
The arrival of the Mariner is the start of operations for the flow of a rocket.
Teams from ULA and NASA's Launch Services Program start by unchaining the Atlas V booster and Centaur components, wasting no time in developing a plan and getting organized for transport.
We're going to take the booster over to the ASOC. It's going to be Convoy 1 to be the leader, followed by the booster.
It's a very exciting day for the vehicle system engineers as we're offloading the launch vehicle that will carry the GOES-S satellite.
Here comes the Centaur second stage, with its pressurized stainless steel tank as thin as a dime. Unable to support its own weight until fully fueled, it's carried off the ship by a specialized trailer. Next comes the Atlas V booster, all 106 feet of it. This booster and 4 solid rocket motors have one job: provide enough energy at liftoff for the entire launch vehicle and payload to overcome the pull of Earth's gravity.
I never get tired of seeing the rockets come in. It's very exciting, especially on the Mariner.
Now on land, a challenging cross-base transport lies ahead to the Atlas Spaceflight Operations Center. Inside this multifunctional facility, crews will remove the protective coverings, inspect the hardware, and install the final flight components. For now, this mission remains a go, but the highly complex job of stacking the rocket is still to come. ODark 30, Cape Canaveral Air Force Station. With a full week of intense rocket assembly activities ahead, the teams from Launch Services Program and United Launch Alliance are getting an early start. It all begins with the booster. The booster is the backbone of the Atlas V, and literally everything is riding on it. It's the largest component and first to be lifted.
The Launch Services Program partnered with United Launch Alliance to select the Atlas 541 vehicle because it is one awesome rocket, and we need that thrust to get GOES-S to its geostationary orbit to meet its mission requirement.
It will take more than just the booster to get all the way to geostationary orbit. That's why we're adding 4 solid rocket boosters.
When you start with the Atlas booster, it's like 860,000 pounds of thrust with just the RD-180. So we need the solids for extra performance. We need it to get heavy payloads off the pad and for additional performance going to geosynchronous orbit or geotransfer. Mating the solids to the booster is a very hazardous operation. We have safety with us at all times. You have 100,000 pounds going up into the air and hanging on a crane. And oh, by the way, it's explosive.
Once the solids are mounted, it's time to mate the Centaur.
The Centaur is the upper stage, and it's tuned. It's like a highly tuned race car. It's light, it's efficient, it performs well for us.
Here to Broad, you do the job and get it done right. You see something that's not right, bring it up to us. Let's give us a chance to fix it, okay? All right, let's get in position to do this thing.
Assembling a rocket can make or break any mission. It takes tremendous coordination and skill to get this job done. The team makes it look easy, but rocket science never is.
The coolest part of my job is coming down here and seeing the hardware and knowing what it's capable of. We all get to work with rockets, and it's really exciting and fun, and everybody has their part in all of that. And yeah, when you're out with friends, you can say you're a rocket scientist. I do.
So there's really nothing quite like all the work and all the setup that we do to get ready to do this and get built up the rocket and test it to get to launch day. And when we get to T0 and the rocket lifts off and the control room rattles and shakes a little bit, it's an awesome feeling. That is the ultimate reward, and that's really what makes us happy, what makes our customer happy, is putting our customer where they want to go in the right spot, in the exact right orbit, and that is, there's a lot of pride in that.
This rocket is almost ready to roll. Of course, the only thing missing is its GOES-S payload. 2 weeks to T0. Today is another huge milestone for NOAA's GOES-S mission.
So today we start something called encapsulation. By encapsulation, we actually put a container around the satellite. It's called a payload fairing. That payload fairing will protect the satellite for the first 3.5 minutes of its mission.